Hello guys, we are coming back for the second video for the haloalkanes, where we're going to continue with the chemical properties of haloalkane. Showing to you right in front here is the mind map for the reactions of haloalkane. You can see that there are so many reactions involving haloalkane that you need to know. So let's, without any hesitation, have a look at the series of the reactions for haloalkane. So if you still remember of how we prepare haloalkane previously, we learned that haloalkane can be prepared from the I'm going to use this pointer. Now you can see that, okay, you can prepare haloalkane by using propane. So you have to use a chlorine under UV to form 1 chloropropane, for examples, okay. And we also learned previously that propene can also be used, alkene can also be used to form haloalkane, where we react with HCl, sometimes in organic solvent, to form 1 chloropropane and 2 chloropropane according to the Markovnikov rules, okay. So one more ways that you have to know on how to prepare haloalkane is from alcohol. You can also prepare from alcohol when you react with a chlorinating agent, for example PCl5, phosphorus pentachloride. You can eventually also form 1 chloropropane. So these are the 3 important ways of preparations for the haloalkane. Then we are going to have a look at the series of reactions for haloalkane. There are generally 5 chemical reactions of the haloalkane, where haloalkane can react back to form alcohol via hydrolysis, where you have potassium hydroxide under reflux. And if you were to, you can also form back alkene, okay, by using not sodium. Strictly in here we uses potassium here, potassium hydroxide in ethanol under reflux, okay. So this is a must. You must use potassium hydroxide in ethanol under reflux to form back alkene. And then haloalkane can also be used to prepare amine. So this is the only compound so far that can be used to prepare an amine. So if you react with concentrated ammonia in ethanolic, you form propan-1 amine, okay. And then if you can also react with potassium cyanide in ethanol under reflux, you first form a butyl nitrile. So the butyl nitrile can be then undergoing hydrolysis to form a carboxylic acid, and also reductions to form an amine. So in here you will note that from propane to become butane, the number of carbon has increased by 1. So later we are going to stress that this is one of the methods to increase the number of carbon by 1. And last but not least, we're going to have a look later on how haloalkane can be used to prepare Grignard reagents when you react with magnesium in dry ether. So this is a Grignard reagent, and Grignard reagents, if you use properly, it can be used to synthesize different classes of alcohol. If you use a methanol, you can use to form butan-1-ol. If you react with ethanol, you can react to form pentan-2-ol, which is a secondary alcohol. And if you react with propanone, you can react to form 2-methyl-pentan-2-ol, which is tertiary alcohol. And eventually when you react with carbon dioxide followed by hydrolysis, you form carboxylic acid, especially butanoic acid, okay. So enough with the mind map. So let's have a look at the content. So first of all, we are going to rediscuss back on the chemical preparations. So as we mentioned just now, the haloalkane can be prepared via free radical substitutions reactions of halogenations of alkane, where you're going to use gas such as fluorine, chlorine, bromine under ultraviolet to give the respective product. So we have already discussed this during this alkane. Maybe you want to look back at the alkane chapter. And then you also have hydrohalogenations of alkene via electrophilic additional reactions. We also have a look at the mechanism previously. So this is how we react. So you react with HCl or HBl in room temperature. Sometimes you might even need an organic solvent. And this reaction react according to these Markovnikov rules. So you have a major and minor products in here. So what is about Markovnikov rule? Maybe you would like to check back on the alkene subtopic last time. And then you have halogenations of alcohols. If you use a halogenating reagent such as phosphorus pentachloride or thionyl chloride under room temperature, you can eventually form these haloalkanes, okay, plus some of the side products. So in this case, if you use PCl5, the side product will be POCl3 plus HCl. As for the chemical reaction of haloalkane, so alkyl halide are easily converted to many other functioning groups. So the halogen atom can leave this bonding pair of electron easily because a halogen is a good leaving groups. So when another atoms replace the halide ion, the reaction is a substitution reaction. So when the halide ions leave with another atoms and form a new pi bond, it is called as an elimination reaction. So in many elimination reaction, molecule is lost from the alkyl halide to give an alkene. So this elimination is also called as dehydrohalogenation because hydrogen halide has been removed from the alkyl halide. So table below summarize some of the basic reactions of the haloalkane. So let's have a look with the tables. Starting from the hydrolysis of haloalkane via nucleophilic substitution reaction. We are going to look into detail later what is a nucleophilic substitution reaction. Our reagent here is either you use potassium or sodium hydroxide in under reflux. So this is the general equation. So if you have RCH2Cl plus NaOH under reflux, you form RCH2OH plus NaCl. So later we are going to discuss in details about the mechanism of the reactions. Then we also have alkylations of ammonia, also via nucleophilic substitution reaction, where our reagents is concentrated ammonia heated in ethanols under reflux. So general equation for the reaction can be written as RCH2Br plus NH3 in ethanol under reflux. You form RCH2NH2 plus HBr. We can also form the nitrile, okay, by using nucleophilic substitution reactions, where in here our reagent is by using potassium cyanide, where we are going to heat under reflux in ethanol also to form nitrile. So this nitrile will further form other substance which we'll discuss in details later on. And then we also have the elimination of hydrogen halide as we mentioned earlier. So our reagent in here is strictly, as I mentioned just now, is strictly potassium hydroxide in ethanols under reflux. So if you have ethanol under in potassium hydroxide under reflux, you form an alkene plus HBr. And last but not least, you have a Grignard reagent, which is the formation of organometallic compounds, where your reagent in here is using magnesiums. So your condition is dry ether in room temperature. Or there can also be another type of the organometallic compound called as butyllithium, alkyl lithium, where compared to magnesium, you require a colder condition, which is negative 10 degrees Celsius. So this is the respective equations for the preparations of the organometallic compounds out from the haloalkanes, which is useful to synthesize different classes of alcohols. Okay, so these are the introductions tables for the chemical reactions of the haloalkane. So without hesitation, we are going to have a look only at one type of the reaction, which is hydrolysis of the haloalkane. Now the term hydrolysis is actually referring to an OH is added or substituted to the reactants involved. So by adding either sodium or potassium hydroxide reflux at 55 degrees Celsius, a haloalkane can eventually form alcohol via nucleophilic substitution reactions. So the general equations for the reactions are expressed below. If you have Rx plus NaOH under reflux, you form an alcohol plus sodium halide. So this reaction can easily occur due to the polar of CCl bond because it is partial positive and partial negative. So this OH minus, which act as a good nucleophile, is ready to attack the carbons inside there. Okay, so by using the unshared pairs of electron and the negative charge. Now the rate of hydrolysis of haloalkane depends generally on two major factors. First is the bond length of the CX. Second is the classification of the haloalkane. So let's have a look one by one. What is this? So consider the bond length of the CX from chlorine to iodine. So given to you, these are the bond energies: CCl 346, CBr 290, and Ci 228. So as we say, is that the bond energy decrease, rate of hydrolysis increase due to when going down to the group 17, atomic size becomes smaller. When atomic size becomes smaller, bond length become when going across group when going down group 17, atomic size become larger and the bond length become greater. So bond energy decrease means that easier for the CX to break. The second factors that influence the rate of hydrolysis is the classification of haloalkane. So table below compare between the reaction of primary and tertiary haloalkane and what are the type of mechanism that each of these haloalkanes undergoes. Okay, we have a primary haloalkane exemplified by 1-chlorobutane. Tertiary haloalkane exemplified by 2-chloro-2-methylpropane. Now note that both of them are structural isomers of each other. So a primary haloalkane love SN2 mechanism, where this SN2 stands for substitution of nucleophile in second order, while a tertiary haloalkane of 2-chloro-2-methylpropane undergoes substitution nucleophile in first order, SN1. So these are the general equations for the reactions, where you have this 1-chlorobutane react with sodium hydroxide under reflux to form butan 1O, while 2-chloro-2-methylpropane react with NaOH under reflux to form 2,2-dimethyl propan 1O, propan 2O, sorry. And let's have a look at the mechanism of the reactions, where you can see in here the nucleophile of the OH minus attacking the carbons in partial positive of the these carbons in CCl bonding, so forming a complex, intermediate complex that force the Cl minus to readily to leave the groups. So this is the intermediate form, and this is a slow step. So because a slow step is a rate determining step, so in here you have both of the reactants in here involved in the reaction, so that, which allows us to call it as a second order. And finally, this intermediate is unstable and tends, CCl, since it has a greater bond length, it tends to break easier and form the alcohol plus Cl minus in the fast steps. Now compared to a tertiary haloalkane, which undergoes SN1 mechanism, unlike SN2, in SN1 mechanism, CCl bond is first broken via a heterolytic fission, okay, where heterolytic fissions is a slow step for the reactions, which enable this carbon to form a tertiary carbocation. Okay, so it is because that it is able to form a tertiary carbocation, which is actually stable. So which is to give the reason why for the second step, where the OH minus attack the stable tertiary carbocation and finally form the alcohol of 2-methylpropan 2O. Now based on the slow step, the rate equation is written as follow, where for primary haloalkane of 1-chlorobutane, rate equation is written as rate equals to K CH3, CH2, CH2, CH2Cl times NaOH, so indicates that it is a bimolecular reaction. Whereas a tertiary alcohol's rate equation is written as rate is equals to Kc bracket CH33Cl, indicating that it is a unimolecular reaction. Now, based on the number of steps, the energy profiles can be sketched below. So, since these reactions of the SN2 takes in a single step, so you have a single bump looking like this. Okay, so the peak of this activation energy is made of the complex. Okay, whereas this SN1 mechanism done by the tertiary haloalkane is carried out in two steps. So when it is carried out in two steps, so you have two bumps in here, and the intermediate is formed in between the bump in here to show that a stable tertiary carbocation is formed during the reactions. Okay, so now we have to know why is it that a primary haloalkane loves to undergo SN2 mechanism, while a tertiary haloalkane loves to go SN1 mechanism. Here I also explain. So the trend of the SN2 mechanism is due to the issue of steric hindrance in the transition state. So we say that a primary haloalkane is surrounded only by two hydrogen atoms. Therefore, it is possible for the carbon to accept a nucleophile attack and form unstable intermediate. However, for a secondary and tertiary, you can see from the diagram in here, you have a bulky surrounding from a tertiary alcohol, which disable these nucleophiles to attack the carbons inside here. So for this reason, we call this effect as a steric hindrance, and the complex is not able to form due to this steric hindrance. So as a conclusion, stability of SN2 mechanism increased from a tertiary to secondary to primary haloalkane. In another word, primary haloalkanes love to undergo SN2 mechanism. So since tertiary haloalkane cannot undergo SN2 mechanism, so tertiary tertiary haloalkane is more preferable to undergo SN1 mechanism. So when we learn about chapter 2 about the stability of carbocation, we said that a primary carbocation is the least stable, while a tertiary carbocation is the most stable. So there is a chances to form a tertiary carbocation in SN1 mechanisms. So greater the number of alkyl surrounding, greater the electron donating effect, the more stable the carbocation form. Therefore, it is easier for the tertiary carbocation to form. So because of this, stability of SN1 mechanism increased from primary to secondary to tertiary haloalkanes, which indicates that tertiary haloalkane will love to undergo SN1 mechanism. Okay, so through all this explanation, hope that you'll be able to understand better about haloalkane. So I'll see you in our next video. See you around. Thank you.